Welcome to this research presentation on statistics, and we're going to do some explanation of important subjects in statistics and research, and they are statistical significance, type 1 error, type 2 error, level of significance, critical value, t-test, and multivariance analysis of variance, MANOVA. And lastly, factor analysis. So there's a lot of subjects, but we will get through it. And after this presentation, you will know what these subjects are. So let's start by statistic significance. So a statistic significance is the degree of risk that you're willing to take, that you will reject a null hypothesis when it's true. So what is a null hypothesis? We had it earlier, but it's a statement of equality. There will be no difference. And we write it like H0, μ0 equals μ1. So there is no difference. Continuing significance means not by chance or probably true. So we say that it's very probably true, meaning highly significant. So the results are highly probable. Okay, so we know what statistic significance is. So what is a type 1 error? Type 1 error and level of significance are the same things. And type 1 error is written like an alpha. A type 1 error, false positive, occurs when the investigator rejects a null hypothesis that is actually true in the population. So a type 2 error, false negative, occurs when the investigator fails to reject a null hypothesis that actually falls in the population. So the first one, we have H0, μ0, μ1. So this is our first hypothesis. So if an investigator rejects a null hypothesis, actually true. So it's actually true, but we reject it. So μ0 is μ1, but we reject it, but it was true. Then we made a type 1 error. A type 2 error occurs when the investigator rejects a null hypothesis that's actually false. So type 1, type 2, type 1 we know that one, type 2 we fail to reject. So we have μ0 equals μ1. This is our hypothesis, and it's actually false, but we don't reject it. We think it's true. This is type 2. Type 1 and type 2 errors can never be avoided entirely. The investigator can reduce their likelihood by increasing the sample size. The larger the sample, the lesser is the likelihood that it will differ substantially from the population. So increasing the sample size is very important. Type 2 error, false negative, occurs if the investigator fails to reject a null hypothesis that actually falls. So type 1, think of true. Type 2, think of false. And type 2 errors can be decreased by increasing the sample size. And type 2 error is written like a bravo. Okay, level of significance. The level of significance is defined as the fixed probability of wrong elimination of null hypothesis when its fact is true. And we write it as a p. And we use almost every time used the 5% value, 5% significance, and significant at 5% refers to the p-value is less than 0.05 or p less than 0.05. So this is how we write it. And this number refers to luck, actually. Critical value. Here we have a normal curve, and this should be somewhat familiar. It's just how we are looking at this one, and we're looking at how the numbers are spread on a axis. We have here alpha, and we have set alpha. And set alpha is the critical value. How much can the data go this way before we need to discard it? So a critical value is a point on the distribution of the test statistics under the null hypothesis that defines a set of values that can call for rejecting the null hypothesis. So we have data here. Most of the data is in the middle. Some of the data will be over, and this is called alpha. And our critical value, this is the point on the distribution. The distribution is this one of the test statistics under the null hypothesis. So it's critical value. Think of when we're going to reject the data. Also see that this one is a one tail, meaning that we only care about the right side, not the left side. In the two tail, we would care about the right side and the left side. Alpha 0.05. T-test. So a t-test is something we use to test the null hypothesis. So procedure for statistic test to any null hypothesis. So this is the steps that we need to do. Number one is statement of the null hypothesis. Example, H0 μ1 equals μ2. There is no difference between the means of two samples. Then we need to establish a risk. So we use type 1 error to 0.05. Then we need to select the appropriate t-test statistics, and we use a t-test. Then we need to obtain value. This is done by computation of the test statistics value. Fifthly, we need to set a critical value. Determine the value needed for detect for the group of statistics degrees of freedom table. Number 6 is compare obtained value and critical value. And 7 is if the obtained value is more extreme than the critical value, the null hypothesis cannot be accepted. So let's do an example of the t-test. It's a bit complex. So a professor started her research with a diet drink that her 10 participants needed to drink every evening for 2 weeks. The participant would be weighed before and after the 2 weeks in order to check the changes in the weight. So she gave her participants a drink and said, you need to drink this every evening, and we will weigh you before the test and we will weigh you after the test. And we will see if you have lost weight or gained weight or the weight is the same, to check if the drink works. Okay, so what hypothesis is the professor investigating? What is the independent variable? What are the levels of independent variables? What is the dependent variable? Which statistical test would the professor use to test her hypothesis? What can you tell about the dependent variable? What decision should the professor make? And here we have some data that we have got in a table from the research. So what hypothesis is the professor investigating? So participants' weight will be the same or significantly higher after receiving the diet drink than they were prior to receiving the diet drink. This is the hypothesis, and this gives the following statement of null hypothesis. H0. There will be no significant difference in participants' weight before receiving the diet drink and participant weight after receiving the diet drink. So statement of equality. H0 my 0 equals my 1. It's the same. This is a directional hypothesis because we state that the group average weight will remain the same or go up after receiving the drink. So it's one way, a directional. Non-directional, that would look like this. Y0 is not Y1. Directional would look something like this. Okay, next question. What is an independent variable? What are levels of independent variables? The independent variables are the variables that the researcher has control over. Is manipulated by the researcher. Independent. It's not dependent, it's independent. The researcher has a control over it. The independent variables here is drinking diet fuel at bedtime. And the levels of independent variables are before and after. Further, there are two levels of independent variable. A, absent of the drink before, and 2, present of the drink after. What is the dependent variable? Well, the dependent variable here is weight. It is something we cannot change. The independent variable we can change. Which statistic test would the professor use to test her hypothesis? Okay, so Salkin in this is reference number 1 on page 151. Difference between two main types or two main groups of tests. The first group examining the relationships between variables, while the second group examined differences on one variable. Okay, so we either have more variables or one variable. Here we have one variable, which is weight. Because of this, we will select the second group of tests. Next, we will ask if the participants will be tested more than once. Here we are testing them 2 times. One before they drink diet fuel and after drinking diet fuel. Because of this, and because we have 2 groups, we go to the subgroup of dependent samples. The requirements are met for t-tests for dependent samples. The researcher should use this test. So we have a t-test for dependent samples. The researcher has selected a small sample with only 10 persons in the group. Because of this, the researcher needs to know that she will select the appropriate test for the research. If she fails to select the correct test, then the data in it Data in and out will be wrong. Okay, this is our data. What can you tell about the dependent variable? What decision should the professor make? Okay, let's start by looking at the data. We have variable weight. We have group before and after. Number of pairs, mean, standard deviation, standard error for mean. We have pair 1 before and after, mean of the pair difference, t-value, degrees of freedom, one-tail p-value and two-tail p-value. So let's start by explaining what all this means. Number of pairs, number of members of the group, number of test subjects. Number of pairs, the first number, 10, is the number of people that we investigated. So the next second number is the mean. A mean is the average, the sum of weight of the group divided on size of sample. So here we have 223 and 224. So this is before, this is after, and we see that the number is quite high, so it implies that it might be pounds and not kilogram. And we see that the difference between before and after is not very high, it's almost the same. 223, 224 is almost the same number. Not much big difference. So the weight, the 10 people before and after, and the difference is only 1 pound. Next is the standard deviation, average variance from the mean set. So how much can one of the test deviate from the mean set? And as we can see, before and after, it's not much difference. Next we have standard error of the mean, and that is variability across multiple samples. This can show how different the population mean can likely be from a sample mean. We have mean of the pair difference, and this is 1.30. How much the mean is when the different groups are paired. So we take before and after and pair them together, and we can see the difference. So try to take 2 to 4.6 minus 2 to 3.3, and you will get this number. We will try that one just for fun. 2 to 4.6 minus 2 to 3.3, 1.3. So the mean of the pair difference. And now we have the t-value. And this one is really interesting. So a high number means that the group differ. This implies that the before and after weight is different. Also, that the weight is higher after the test than before. So if it's a high number, the weight is higher. If it's a low number, the group is similar. This implies the measurements weight before and after the experiment are equal. The drink doesn't affect the weight. The degrees of freedom is the number of values that can differ before breaking constraints. Next we have the one-tail p-value. Because we are stating a directional hypothesis, we will use the one-tail p-value. Okay, you're coming out more strongly. So what this means is one-tail p-value. So we have our normal distribution like this, and we have here and we have here. So this means if they're on this area, they are losing weight. If they're on this area, they are gaining weight. So set alpha here and set alpha here, minus and plus. So we are only interested in this area, that there are we are just using one tail. If we are using both tails, then we would use both areas, both the left and the right side. But we are only interested in the right side. Because of this, we are using one tail p-value and we will ignore two tail p-value. This meaning that we are coming out more strongly. So if p is less than 0.05, we will reject the H0 hypothesis. If p is greater or equal to 0.05, we will accept the H0 hypothesis, and this means that we will fail to reject. There is no difference. Okay, I have explained all the numbers, now we can look at them. Okay, and I will just take the two-tail p-value also. If we were used a non-directional hypothesis, we will use the two-tail p-value. We will test the relationship both way, gain and lose weight. And then we could say like this product might work. For example, people will lose or gain weight. Okay, let's look at the numbers. Number of pairs. Well, that was the easy one. It's 10. 10 people. The mean. The difference between the before and after is 1.3. It says a down mean of the pair difference. This means that a group of 10 people have gained 1.3 after drinking the drink. They have not lost weight. Standard deviation. It was average variance from the mean set. So the difference between those two numbers is 1.0452. This implies that there are only one indifference between the difference from the mean. So there is not much difference in the group. So if one person lost like 10, the deviation would be higher. Here we can see that the deviation is just 1. So there is not much deviation in the group. Standard error of the mean. It's variability across multiple samples. This can show how different the population mean can likely be from a sample mean. Mean of the pair differences. How much the mean is when we difference groups are paired. So this is these two numbers. The mean, this number minus this number, is the mean of the pair difference. So investigating this further, we look at the mean of the pair differences and see that the average difference between the before and after weight represents an average gain of 1.30 pounds. So they have actually gained 1.3 pounds on average in these 2 weeks. Okay, the t-value. High means a group differ, and low means the group is similar. High differ, low similar. Okay, if it's high, this implies that the before and after weight is different. Also that the weight is higher after the test than before. Low, group is similar. This implies that the measurements weight before and after the experiment are equal. The drink doesn't affect the weight. And we have 2.053 pounds, which is a small number. The group is similar. It's not different. Degrees of freedom. It's the number of values that can differ before breaking constraint. So this means that 9 numbers can differ before we break constraints. So out of 10 pairs, this is 9, meaning that 9 values can differ before we break constraints. So let's have a look at the one-tailed p-value. Because we are stating a directional hypothesis, we will use the one-tailed p-value. This means that you are coming out more strongly. If p is less than 0.05, we will reject the H0 hypothesis. If p is greater or equal to 0.05, we will accept the H0 hypothesis. This means that we failed to reject. There is no difference. Here the number is 0.035. And so we will test the p-value. So if p is less than 0.05, we will reject. If p is greater or equal to 0.05, we will accept. So we put, instead of p, we put the number here, 0.035, less than 0.05, reject H0. So here, 0.05 is greater than 0.03. If you take away the last number here, it will be easier to see. I will take it out here. And we can even take out these numbers. So just look at this. Look at 3 and 5. And of course 5 is bigger than 3. So we will reject the H0 hypothesis. Okay. From before, we know that H0 is that there is no significant difference for overweight people drinking diet fuel before bedtime. Okay, our conclusion then, this means that there is no difference. The drink does not work. The group didn't lose weight. We can see that 0.35 is less than 0.05. We need to reject our H0. Okay, then we can have a look at the two-tailed p-value. And as we said, if we were using a non-directional hypothesis, we will use the two-tailed p-value. Test relationship both ways. Lose weight, gain weight, both ways. This product might work. But we are only interested in losing weight. We are not interested in gaining weight. So we will not use the two-tailed p-value. Okay, a t-test is very good when you have one variable. But what if we have two variables? Then we need to use MANOVA. And MANOVA is called multivariate analysis of variance. So multivariate analysis of variance, MANOVA, examines whether group differences occur on more than one variable. And MANOVA takes into account the relationship between dependent variables. And this is the formula. It's not very important to know it directly, but it's good to have seen it. So true type 1 equals 1 minus alpha k, where alpha is the type 1 error rate and k is the number of pairwise comparison. Okay, so that was MANOVA. If you have more than one variable, use MANOVA. Factor analysis. Factor analysis reduces the number of variables that can represent a particular construct and then use factor scores at dependent variables. So factor analysis reduces the number of variables that represent a particular construct and then use factor scores at dependent variables. So that was it. A quick introduction to some important statistical terms that you need in your research. So good luck.